Hello friends, here I'm going through the Reasonend Schemer book using core.logic. I just make a video while I do it and sort of talk about my explorations while I kind of engage with the ideas. This is just, I'm thinking why not make a video. So the basics, I already went through some of the stuff here. In logic, you say run, you assign some logic variables, and then you add goals. This here is a goal that unifies Q with this rounded symbol 1, and then there's one outcome. You can have multiple outcomes. This is the disjunction. You can do that with cont E or in logic or, and this is already sort of logic programming kind of thing. That Q is sort of two things at the same time, or there are two branches where Q is different things. So that's the disjunction and the conjunction. It is that Q must be, or that there are multiple goals that must both be true. And this one, for example, doesn't have a result because Q is not 1 and 2 at the same time. It's impossible. This is here, this would be the same syntax. Just the body of a run basically is a conjunction of goals. And then it becomes more complicated. And we can say that with cont E we combine the two, so that every element in the cont E is basically one disjunction, so it's a little bit like the branches, I think you could say that. And yeah, then you could have something else true, like I could say succeed, then this would succeed, and so this is a goal that always succeeds. And cont E, yeah, I can make another one that always fails, and this branch basically doesn't work because all these need to be true, as if they're basically conjunction. It's a conjunction of these two. So this is never true, and something else like this. This would say that 3 is also allowed, so 1 and 3 are both allowed. And now it becomes cool that this goes into data structures. So you say AQ, for example, unifies. I think this is called unify, or it's of course not an assignment, but de facto it's a little bit like assignment. Yeah, how is this called? I know that 2 logic variables are allowed to fuse. So here what do they call fuse? Fuse different fresh variables. Yes, you can fuse different fresh variables like this. Q, then you make fresh. This is a little bit like a let, where all the variables here are new logic variables. Unify X and Q. Okay, now X and Q are fused, so Q is just a fresh variable. And what you could do is you unify X with 10, and then of course the only solution is that Q is also 10 or like this. Fusing them. Okay. I want to check out what the name is for the equal operator. I think maybe this is called unify. Ah, it's just equals. Okay. You pronounce this equals. Okay, good. Good. Okay. Equals. Alright. Okay. So now you can say something like this data structure, this vector here equals A11, and this is a cool thing about miniKanren and core.logic. This basically has this unify behavior where it figures out that this equal works if Q is 11. So yeah, this is kind of cute. And then you can have something like this. Let's say there's also a B, and you can say, you sort of say that if B is 20, then Q is 11. But otherwise you can also say that sort of if B is 30, then something else is true. or it just succeeds. B is also 30. So now there are two branches that work. They are disjunct. So it's either that B is 20 or that B is 30. And in the branch where B is 20, Q is also assigned to 11. And otherwise, Q is still fresh. So the outcome is that we have one outcome where... so the outcomes are... The first outcome is that B is 20. I flip this here. So I say 20 and 11. The second outcome is this thing that... So this is 30 and Q is still anything. So that prints like that. So the outcome is this. I think it should print like this. I make vectors out of these. So yeah, very interesting. Yeah, here it can become something like this as well, of course. Oh, what? Ah, here's something. So now Q is A and B. Q is the vector A, B. Sort of grounded, I guess. I'm not sure if grounded is the name they use. Ground value. Okay, I think that this would be a ground value. I guess ground is the opposite of... Well, ground is just a value, I guess. There are also the logic variables that are fresh, then they're still allowed to mean different things. And I guess there are also logic variables that are allowed to mean only some things. I'm not sure what that... Here I kind of say that B means 20 or something. No. Okay, so this is this conjunct, the two-argument conjunction. That is the same as the AND in core.logic. Oh, it's de facto the same. And then here goal 1, goal 2, goal 3, and so forth. This is the conjunction. Saying that this is a goal that only succeeds if all the input goals succeed. Like AND. Like saying Bob is gray and Bob is a scribble or something. And then the other one is the disjunction. This is like L or... So now all of these are kind of allowed to be true. So it's a little bit like there are 3 branches, I think, for these goals. So it is a goal where either of these is true, I guess. So if you say or Q is 10, Q is 11, then sort of both branches are still valid. This goal succeeds. I guess with 2 sub-goals or something, like, I'm not quite sure. But if I also say that Q is 10 as another goal, then it basically narrows it down, and sort of this one was thrown away, and this whole thing only succeeds if Q is 10. Yeah, here you have this. This is the same, where you say that Q is both olive and oil. Both goals contribute values. Succeeds, saying it's olive succeeds, and olive is the first value associated with Q. Oil equals Q also succeeds, and oil is the second value associated with Q. Okay. Okay, so I went through these as well already. And that is that. We make fresh variables, and then we make some sub-goals. The teacup, you can define this in closure with a closure function, I think. So here's one way to define it with a closure function. So tcup takes a logic variable, like x, and then says that x is either t or cup. So I can write cont e, x is t, and then or x is cup. So this is one way to write tcup. If I say now logic run and say tcup q, that is both t and cupos. Wait, it's nothing. I did this wrong. I had the conjunction instead of the disjunction. Okay. But there's alternatively you can also write this with match, and there's basically there's basically a macro for this part, more or less, I think. And it actually also does more. It also does the match, supports the match, but this is a def ne for making a cont e, basically. Define a goal function, supports pattern matching. All patterns will be tried. See cont e. And for this, I say x, and then I put a list of patterns, and it would just be like this tcup. I think. No, wait. I think it works like that. I say a list of patterns and bodies, and this is the kind of funny thing. No, this already is the thing. Like, oh wait, I'm not correct. Let me quickly check where they use it. Look here, how to do that. A list, and then an argument list. I made variables called t and cup instead of pattern matching to the symbol t and cup. Like this? Yeah, this also works. And it's the same. It is basically the same. No, it's strictly, I think it has the exact same semantic for sure. It's a disjunction where x is both t and cup. Yeah, and now you could write basically goals. You could write goals here, more goals. Yeah. I could say here not equal. Or if I say here fail, then it will never be a cup. Yeah, like this, for example. It would basically try cup and then have a failed goal and not succeed. And yeah, if I narrow the q down here already or something, I say that q is cup. Now it will just fail. And if I do something else, like I say q's a tcup, and then I also say container. I don't know. And cup, for example, is a container, and market, I don't know, is a container. No, I also say that q is a container. No, I get the what doesn't work? So I have here the wrong syntax, I think. I needed a list. I needed a list of. Yeah, whatever. That's just the syntax. Okay, cup. So you find the overlap. No. Yeah, because these two are basically the conjunction of tcup and container. Because I say both tcup and container are true for q, and then in effect we have a search that says that I look for a value of q where this is true, where both these two things are true. So it's a tcup and a container, and then in effect you find this overlap. So yeah, this is how far I am, more or less. And basically I want to start understanding how you program with these possibility spaces for variables, and then I think you probably need to know a little bit how the engine works in order to know how to narrow it down so that you get something that doesn't explode in its search space, because this is the problem. It's easy to express your problem in logic programming, but it's hard to express it in a way where it runs fast. And this is kind of funny how the problem is somehow a little bit different from normal programming. Usually it's hard to come up with an algorithm for something and then later you can optimize the performance, but usually usually you have good performance because you came up with an algorithm that doesn't do much extra stuff or something. But with logic programming, it's easy to say what the problem is, but it might be that you have an exponential search space or something, and basically, even though you said correctly a possible solution, it's no. Okay, that's kind of my state. Here's a teacup, and so here, and then cond E. Cond E is, I guess, the sort of the primitive thing that you built the code out of. Okay, let's continue. Okay, this is about the data structures and the lists. I also went through this already. Teaching old toys. Yeah, maybe I go a little bit fast now through this. Oops. Okay, well, yeah, I can write a list. Lisp grape, raisin, pear. This grape. Oops, I can't, das nächstes ein Closure. First. Yeah, okay, I'm skipping through this a little bit. Okay, now logic, run, make a queue. Now say logic first row of a list, acorn. Say that Q is first row of acorn, then Q is of course A. What is this acorn? A. So yeah, you can also do this. Now Q is still fresh because this goal succeeds. So there's just a goal here that succeeds and nothing else, and then Q is still fresh. L run R. Fresh X Y L first row. Now a list with X and Y. No, with R and Y, and X is the first of these. So X is now R. X is fused with R, and Y is still fresh. And then you make a second goal. So the body of fresh is a conjunction. So both these need to succeed. And now I say that X is peer. So I fused X with R, and now I say that X is peer. I fused peer X with peer, and so R is just peer. Def PR freshly. So okay, this is the definition of this. I can write a function called my first, or I can't call it how. So this takes a P and an A, and then yeah, this is where things become really strange, kind of. Or it's you always have three things. I feel like in relational programming, there's sort of the inputs, and then there's kind of like the output. So it's kind of you sort of have both sides of the equation that you talk about. Usually you have only the inputs and your algorithm makes an output. But in relational programming you have the inputs and the output that you describe. And so this is kind of the big difference, I feel like. So we talk about this. We talk about what is the output of something by saying, now we say D because we don't need D anymore afterwards, I guess. Yeah, let's write this. So wait, that is that we say that when I say that, one sec, what do I want to write? Caro of a list is something. Then P is the list and A is the something. So the first argument is the list, and the next argument is the something, and that is D. One sec. I feel like I make a mistake. I feel like that D should be the list somehow. No, P is the list. So P should also appear as the list, I guess, right? Yeah, I make this mistake. I make the mistake of ignoring. I need to also build a list here. I think there's a control. Yeah, or you say, I think, I say list. yeah, the first element is A, that's for sure. And okay, I'm looking at this. So you say freshly, then equal cons A and D is P. Okay, wait, cons. Let me quickly. Console X also exists. Okay, so console with Q and then with the rest of the list. So D is the rest of the list. So 2, 3, and then you say the list is list 1, 2, 3. This, for example. So can't I basically just take this shape and then I'm cheating because I interpreted, I defined it in terms of console. I want to make the exercise of defining console myself. So in terms of first store. Yeah. So you take this third element in the equation and call it D, and you say that make a and let me quickly check in core.logic. They talked about the differences with cons. There's L-con, there's also L-cons. I should use L-cons, okay. Closure has a way to correct pairs, sequences of improper pairs. Yeah. Core.logic, L-cons constructor, but this behavior list. Okay, I think I should use L-cons, maybe. Yeah, I'm going slow. So if I say L-cons, Q, and then list 1, 2, 3, then wait, L-cons need 2. Like construct a sequence A with an improper tail, D if D is a logical value. Okay, D, but D is a list now. And this doesn't look. This is not a. So this is just not a goal. I think. Yeah, you would need to say that this is true if this is equal to 1, 2, 3, right? Yeah, like this. Okay, so now I can basically write. This is maybe my carbon. Sure. Yeah, my carbon. So you kind of have these three things in the mix here now. Sort of the rest of the list, and the first element. And basically you want to give an interface where yeah, you expose for Caro you want to expose not this tail, but only the list and the thing. So yeah, this should be Caro P A. Yeah, okay. So this is saying that A is the first element of P. I'm saying that there exists kind of a tail where L-cons QD is exactly the list P. Yeah, pretty sure I got it correct now. It's saying that pretend that there exists a D, right? That when I say, oh wait, cons A and D, oh wait, no, the other way, this is the other way around, is it? No, it's this way, it's this way. So L-cons works. Maybe this way around, it's easier to read. I say take an item and add it to some tail, and this tail is just imaginary or is like temporary. and that is equal to the list. So we kind of talk about the tail, but we don't talk about the tail. I don't know. It's interesting. Okay, so this should be a goal now. If I say 1, 2, 3 and Q should be 1 now, right? Yeah. And this is also how first works. Yeah, okay. This is the same. Okay. I implemented first. Nice. What is unusual about this definition? They asked this without an answer. What is unusual about this? That yeah, I think that usually you have, I mean, without relational programming, you have an algorithm that defines take a list and take the first item of a list. But here we have not a recipe. Well, we have sort of a recipe, but for the structure of the data. We have a recipe for the structure, but not for the how to do it. We describe the structure, but not the how to do it. This is the difference, I think, which makes it interesting and higher level. Makes it different kind of programming. Okay, what is the value of yeah, sure. Okay. Take the first. I'm gonna use vectors now. I think I'm not allowed to use vectors though when I read this. In general, you should not use vectors when working through the Reasonend schema. Use list or quoted list. Let's see how far I can get with using vectors. Okay, this is great. So now you have a second list, A, B, C. This is A, and now you say cons. Yeah, this is there's a cons cell. This is so it's not how it works. I forget how to. This, for example. If I use the logic icons. Yeah, this is kind of like a cons cell like that. And they have a list here. Okay, I should use logic list, I think. Okay, wait this. Wrong number of argument paths to list. So this doesn't have this, so then here this, yeah. Whatever. Yeah, like this. Okay, this is a Lcons that also is allowed to have variable tails, improper tails that are logic variables. That's the difference. Because otherwise I have a vector, for example, enclosure, but vectors don't have, I guess, the rest of a tail. You need some kind of implementation for that, to say that this is supposed to be a logic variable. Because I can have elements that are logic variables, but I'm not sure if I can talk about the tail. I think this is the difference. So that's why we use this, the logic icons. Otherwise it would be closure data structures, but I think we need this part with the tail somehow. What is the value here? Okay, take this. 1, R, then fresh, X, Y, then first though, I'm gonna use vector here. Okay, so this here already is grape, so we assign X to grape. Then we do another one. And here we assign Y to... Oh, I should have these lists here. Okay, let me use list. It needs to be like this. Okay. And then there's another goal, and these are, of course, these are the conjunctions, so all of these need to succeed. And here we say... So yeah, we say this is equal to... Here I can use a vector. Yeah, x, y, r is equal to... Oh wait, x, y is r. Okay, this is kind of like saying, the output of my logic run, the R is the vector x and y. Also here, this needs to be first. So grade A, but I made some mistake. A, this was not supposed to be a list. Why is the first here? So, true, this was different. Okay, wait, this was different. I should have said L cons, x and y are, and this, yeah, now I get grade A as a list. Okay. Why can we use cons in the previous frame? What do you mean? Why is a list A? Because variables by fresh are values, and each argument to cons can be any value. Yeah. What is the value of color? No, that's the same as saying rest. Grade raising peer. So this is a list raising peer. What is the value of? Yeah, okay, whatever. Okay, let's write it. Okay. So 2 times rest. Isn't this called R rest? No, no enclosure. Enclosure use n when you do that. No, you say env. You say env or you drop 2. That's what you. That's what I would do. But yeah, you can also call rest. I feel like there's something like rest. Next. So next. Does this exist? Yeah. A, B, C. Yeah, that's C. And this is the same as calling rest 2 times, I think. Next. No, yeah, it calls next 2 times. It's almost the same as rest. There's actually a difference there. Returns a seek of the items after the first. Calls seek on its arguments. There are more items returning and rest. Returns a possibly empty seek of the items after the first. Calls seek on its argument. Man, this is almost the same thing. More is. Yeah, actually not entirely sure what the difference is between closure RT next and more. I would expect this to be almost always the same. If it's an I seek, return next. If it's an I seek, return more. Okay. Then call seek on the outcome. So this returns a persistent list empty if seek is null. It's different. Here returns null. But yeah, it's also depends on the implementation of more as well. However, the sequence is implementing more or next. It's kind of up to the implementation. It's actually different. Okay, I think I should call rest 2 times maybe. Then it is born. First of this is O. Okay, now logic run R. Then fresh V. Then say first O. Now say A corn. Okay, V. So V is A now. Then fresh W. Say resto. The W is the rest of. One sec that. Wait, how does resto work? Resto. Okay, so there's a list 1, 2, 3, and then Q is the rest of the list of 2, 3. Okay, so now I say that V is the first of A cons, or this is A. And then here I say that V is a list where W is the rest. No, color, yeah. So this is, I think somehow strange. This part. Unnesting fresh expressions, that's really unnice. Then we can just code. Oh wait, I can't copy it with this PDF reader. Sec. fresh coulda W. The coulda of V is W. I say here coulda. Oops, I was wrong here. That was resto. Okay, now things make sense. So V is corn. And now I say the rest of this. So this is like calling rest 2 times. It's a little bit like calling rest 2 times. So W is now on. Yeah, and then Caro is R. Okay, so we kind of say that R is now the first of the. So here first O is R. So A will R. The outcome is O. Yeah. The process of transforming is called unnesting. We introduce fresh expressions as necessary as we unnest. Yeah, and core.logic has this pattern matching built in, so in core.logic you can do this, for example, with this match E, and then I need to remember the the syntax. I'll quickly do I have an example. I have an example. I also have examples in my advent of code explorations. Oops. Yeah, let me. Here's an example. Okay, so I would say this also introduces automatically new fresh symbols. Okay, and then it always goes in these both directions. So you can say match this list acorn and say that will this work? This is a sequence. I'm not sure if I say sequence or vector here. Where this is R and then anything. I think you can say throwaway variable. Wait, I need to say I need to get to the O. So I say throwaway, then R and then some rest. Yeah, this is correct. Yeah, this is the same thing with pattern matching. Yeah, it's quite cool. Define CUDA rule. Okay, I'm gonna try to define my CUDA rule. Okay, so I'm gonna look at how. So yeah, this is yeah. Okay. Okay, wait. It is this, but I've flipped these here or something like that. 1 sec. I'm gonna give this names. Here's the list, and here is the rest of the list, right? So when you say cons an item to the rest, yes, but the item is kind of, we don't talk about the item, it's this whatever item, then that is the same as the list, yeah, like this. So I talk about the structure of what this rest is, kind of like. I'm pretty sure this is correct. So I say my CUDA, then yeah, okay, here I say 1, 2, 3, R. So this is 1, 2, 2, 3. Yeah. You can also I can also say here Caro. This is the built-in implementation, and this is just the same. Oh, that doesn't work like that. So not Caro. Resto. Enclosure. Like this succeeds. Yeah, it's fascinating. And yeah, with pattern matching. Because with pattern matching, this is maybe also crazy. So you have you have a list and you have a rest, and then the solutions are something where there's a. So yeah, oh wait, 1 second. So yeah, the rest is this. And man, this is so weird. Like this, right? Like this, yeah. Man, this is. But the okay, wait. Also, I need more vector. This is the second version, and that also works. Yeah. Well, this is the same thing, pattern matching. Yeah. And this is even more ergonomic, I think. But yeah, it's of course it just has a different concept. This pattern matching thing. But this under the hood is doing the same. It is kind of making a variable that is for throwaway and unifies with anything. Yeah, for example, this is what I did here with the A. And then it says that this thing unifies with this throwaway thing at the rest. And so this is kind of this part a little bit. And that's it. That's it. That's so strange that. But we also gave a name to this the rest. So, and we unify this name with the second input here. So there's also this unify with these two, something here, something like that. It can make sense that it's easy to define it in terms of pattern matching, because it's kind of the primitive. The coulda rule function is kind of the basic way that the pattern matching works in the first place. So exactly because of this thing, the pattern matching works in terms of unnesting, in terms of resto and firsto, I think, conceptually. I guess internally it uses maybe something more smart with this unify or something like that. Okay, what is the value of first, rest, grape, raisin, pear? Okay, this is raisin. Cons. I'm using this icons. What? Can I already do this? First of a list, this is a list, A and B and C. Okay, sure, this is raisin, pear. I did something wrong. Should have said rest? Wait, give me the rest of. Also, not first. Wait, I think I read this wrong. Okay, raisin, pear, A. Okay. What is the value of this? Okay, let's type this. Run R. Oh, this is. I need to. Oh, yeah. I copy this. I don't know why the text comes also squashed in the PDF here. This is this is really hard to read for me. Okay, I'm gonna type this one in myself. Okay, so say fresh x y. Now I say resto grape raisin pear x. Okay, so x is raisin pear, the list. Then I say firsto. And didn't I already do it? Wait, I feel like Jesus, didn't I already do this? Isn't this almost the same as what I did up here? No, whatever, let's do this. Here I can also do the same thing. B and C is Y, and then logic, L-cons, X and Y is R. Okay, so R is an L-cons of X and Y, X is raisin and pear, and Y is A. This is a list raisin pear A. It's a list, so it's the same as this one. The first item is the list raisin pear, and then the next item is A. That's the same. yeah, okay, you also see how it sort of looks like the same. Rest and first, and then you kind of, here, this is a little bit of ceremony in this case, to sort of give it an output, to extract the output a little bit, but yeah, the thing is basically the same. Okay, first to a corn, so first to acorn, corn. Also could have, man, I always use this one. Resto. This is true, this is just true. What is the value associated with Q? Nothing, still fresh, because this succeeds. What is the value associated with X? Here, okay, run. X, resto, corn, and then make a list with X, R, and N. Ah, that's interesting, I guess. Yeah, this would say that this would succeed if X is O. Oh, does I make some mistake? I make some mistake. On. Can I say O R N? I guess this doesn't work. Also this doesn't work. I guess this doesn't work. So I need a middle here, I think. Yeah, this was proper to make it a proper list. Yeah, okay, sure. Yeah, like this again. X is O now. Okay. But yeah, I think that in core logic you probably use the pattern matching. I keep going to that then for these things. I think I would say that corn, and then here I would say that is X, and then R, and yeah, like this. Oh wait. Oh, resto. Oops. I also said resto. You can wait in order to be. Something else you can do is you say, give me the rest, and this is basically the conjunction of two goals now. In that case, that's why you need this additional parent here, because I can have more goals. I think this should work with it. Now I say that XR is so I guess it would look like this. X, R, and okay, like this. Yeah, it's the same. Also, it reads almost the same. And I sort of get rid of these, building these lists there, I guess.